5.3 Properties of rational functions. So sadly, we can't go beyond just properties. We don't learn to graph them, which is sad because I love graphing these. And every semester, I wear a shirt. I wait all semester to wear this shirt, and I can't wear it because you can't see me. But I will tell you what it says because it's totally appropriate. And you can imagine wearing it at school how funny it is. Okay, so we're gonna learn about asymptotes today. So this is what my shirt says, and it has like a graph on it and everything. So it says this. Alright, so that's what it looks like. As you can see, that's funny, right? But I can't wear it for you, but that's exactly what it looks like. It's a blue t-shirt with white and yellow text. But at least you got to know it exists. It's in my closet. Alright, let's get started with the notes today. I guess I don't need to erase that. We're not going to see it. Alrighty, so 5.3 Properties of rational functions. So a rational function is a function of the form r of x equals p of x over q of x. Now what the heck does that mean? Well, it just means function over function. So equation over equation, but the equations have to be functions. So you can't have like square roots or anything like that. You can't have like weird negative exponents, nothing like that. P and Q are polynomial functions, and Q is not the zero polynomial, meaning bottom can't be zero. The domain of R is a set of all real numbers except those for which the denominator Q is 0, so we set the denominator equal to 0. So a rational function is when you have a fraction that has a polynomial on top and polynomial on bottom. The domain is all real numbers except the number that makes the bottom 0. You set the denominator equal to 0 and solve, exclude that value. Horizontal and vertical asymptotes. So I'm going to not use the math talk. This is very, very math talk. Right? We're seeing limits, we're seeing infinities, we're seeing weird things that we haven't seen before. So I'm just going to try and explain this as best as I can without doing like major crazy math talk. All right. So this is our end behavior for rational functions. And when we have a horizontal asymptote, it's just going to approach that horizontal asymptote. So you see here how it's like just approaching the asymptote, so it's just going to approach it. Same thing here. That's all it's saying. And this one is x in the positive direction. This one is x in the negative direction. That's all that's saying. See? As x approaches infinity, it's just going to approach the asymptote. As x approaches negative infinity, it's just going to go towards the negative asymptote. When you have vertical asymptotes, as it approaches infinity, they both go, it's going to go up towards the asymptote, and if it's approaching a vertical asymptote where you have multiple, it'll look like this. This is really calculus talk. I just wanted to introduce it to you, like approaching, what does that mean? Now let's get into normal stuff. So locating vertical asymptote, also known as the VA. The graph of a rational function in lowest terms has a vertical asymptote x equals r if r is a real zero of the denominator q. That is, if x minus r is a factor of the denominator q of a rational function r in lowest terms, the graph of r has a vertical asymptote x equal r. That's just the domain. The vertical asymptote is the domain. But in lowest terms, you see how that's italicized? Why? Well, because what that means, that's a new phrase for us. It means to simplify. So what it means to factor everything and simplify. Then find your vertical asymptote, which is just your domain. So in order to find our vertical asymptote, we just find the domain. So we see if we can factor. If we look at f of x equals x plus 5 over x minus 3, we can't factor that. So to find our vertical asymptote, we set the bottom equal to 0. So we get our vertical asymptote as x equals 3. At the end of this video, I'm going to go into a little bit of extra detail about asymptotes. So stick around if you're going to go to pre-calc and calculus and stuff like that. But if you're going on to stats or like something else like that, you don't need to stick around. All right, next one. We can factor. We can factor this. All right, well, we can't simplify. We can factor, but no simplifying can be done. So what we're going to do is set the bottom equal to 0. So since we have two terms, we have 2 that equals 0. So we have our vertical asymptote at x equals 7 and x equals negative 7. Again, at the end of the video, I'll show you what that really means, what it looks like, what are we talking about, why is that the domain, okay? All right, so next, we cannot factor because that's not a minus, so it's not a difference of squares. So since we can't factor, we're going to set the bottom equal to 0. So let's go ahead and subtract 9. I can't solve that. You can't take the square root of a negative number, so it's no real solution, meaning you have no vertical asymptote. It's possible to have no vertical asymptote. All right, last but not least, we can definitely factor this because the top is a difference of squares. And the bottom, we can just factor straight up. We can factor that into x plus 7 and x minus 5. Here we can simplify. So when we simplify, what we're left with is x plus 5 over x plus 7. Now we can go ahead and find our vertical asymptote. So we have 7 equals 0. So our vertical asymptote is x equals negative 7. All right, if you're curious and if you're going to pre-calc, wait till the end of the video and I will show you graphs and what it means to have an asymptote or not, okay? All right, other types of asymptotes, horizontal or oblique. It's either or, horizontal or oblique. It's never both. It's either horizontal or oblique. Vertical is just vertical. So that's its own category. So we have category 1, vertical asymptotes. Category 2, horizontal or oblique. All right, so all this is saying is that we have a rational function. That's all this top part is saying, is that we have a rational function. So if you have the rational function, you can figure out stuff about the asymptotes. The degree of the numerator is called n. The degree of the denominator is called n, or m. So property or rule 1. If the degree of the numerator is less than the degree of the denominator, the line y equals 0 is a horizontal asymptote. So if the degree is less than, if the degree on the top is less than the degree on the bottom, your horizontal asymptote is y equals 0. You don't need to do anything. It just is. If the degree of the numerator equals the degree of the denominator, your horizontal asymptote is leading coefficient over leading coefficient. I like to say that it is LT over LT, leading term over leading term. Things are going to cancel out. You're going to be left with coefficient, but you'll see why in a second, why I said that. All right, if n equals n plus 1, so if the degree of the numerator is exactly 1 more than the degree of the denominator, the line y equals ax plus b, that's the same thing as mx plus b, is an oblique asymptote, which is the quotient found using long division. An oblique asymptote is diagonal. If the degree of the numerator is 2 or more greater than the degree of the denominator, there are no horizontal or oblique asymptotes. But we can figure out how it looks. So to find the end behavior, so for this one, we have no horizontal asymptote or oblique asymptote. But we can find end behavior. And that's what asymptotes do. They help us guide the graph. So if we can guide the graph, just like when we were graphing exponents, how we had those asymptotes where it never crossed that asymptote. Same thing here. That's going to help us guide that graph. Again, a rational function will never have both a horizontal asymptote and oblique asymptote. It's one or the other. Alrighty. Finding a horizontal or oblique asymptote, so find it if it exists. So the first thing we need to do is find the degree of the numerator. The degree of the numerator, that's n. So the degree of the numerator is 4. Now we need to find the degree of the denominator. The degree of the denominator, that's we say is m. So the degree of the denominator is 3. So you see how the degree right here is exactly one more than the bottom? So let's look. The degree of the numerator is one more than the degree of the denominator. That's rule 3. So we're going to be using rule 3 here. Rule 3 states that we have an oblique asymptote at y equals ax plus b. Mx plus b, ax plus b, all the same stuff, people. So we find that using long division. If you cannot remember long division, I do have a video for it on my YouTube. Just scroll through all my videos, you'll find it. So the top goes first inside the garage, inside the house. And remember, we have missing values. It goes 4 to 2, so we don't want that. So we have 3x to the 4th plus 0x cubed minus x squared minus 0x minus 0. Anytime you have a missing part in the order, so it has to go 4, 3, 2, 1, nothing, you want to put a 0 there. You don't have to, but it definitely helps when you divide. Alright, the bottom goes outside, so we have x cubed minus x squared plus 1. For the outside, you don't have to put missing values. It's just the inside, put those missing values. So what's great about this is that once you get ax plus b, you're done. We always look at the first one. So by multiplying, what can we do to multiply to x cubed to make it 3x to the 4th? Well, it's missing a 3. And then x cubed to x to the 4th, we need an x. Now we multiply it back out to everything. And when we do, we have 3x times x cubed is 3x to the 4th. 3x times negative x squared is negative 3x cubed. 3x times 1 is 3x. We put it where it goes in the proper column. So we put it with what it's alike. And then from there, we're going to go ahead and switch all the signs. So positive becomes negative, negative becomes positive, positive becomes negative. And the first term will cancel out because that's 3x to the 4th minus 3x to the 4th. That cancels out. So we bring everything down. We're left with 3x cubed minus x squared minus 3x. And we don't need that 0 anymore. Now, you see how we have this part? Now all we need to do is find the b part. So same thing, first one. How do I make, by multiplying, what can we do to x cubed to make it 3x cubed? We just need to multiply by 3. Guess what? You're done. That's the b. You're done. Your oblique asymptote is y equals 3x plus 3. You do not need to keep going. You just need to do it twice. Done. Unlike the video that I have for this, unlike how you were taught how you had to keep going until you got a remainder, this, we're done. You just want number x, number. That's it. So it's a lot less work. All right. If you need help, look at the video on my YouTube for dividing polynomials. Because that's something that you need to have learned. So look it up, or just look up any video on YouTube. It's going to be great, okay? Let's find our horizontal or oblique asymptote. So first thing we need to do is the degree of the numerator. That's 5. The degree of the denominator, that's 3. So it's 2 more. The degree of the numerator is 2 more than the denominator. So if we look at our rules, that's rule number 4. So rule number 4 states if the degree of the numerator is exactly 2 or more greater than the denominator, you do not have an oblique asymptote or horizontal asymptote. So that technically is our answer. But we know a lot about what we just were given. So we can determine M behavior, and M behavior is leading term over leading term. So that's 2x to the 5th. Okay, just move that out of the way. 2x to the 5th over x cubed, we can simplify. And we're left with 2x squared. So what that means so the graph will behave like y equals 2x squared as x goes towards positive and negative infinity. So what it'll look like this. Whatever is in between is in between, but the ends will look like this. They will go up and up. How do I know up and up? Because it's an even and it's positive. The exponent is 2, and it's a positive 2x squared. So it goes up and up. All right, example 5. So let's find our degrees. The degree of the numerator is 4. The degree of the denominator is 8. So the degree of the numerator is less than the denominator. So when the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is y equals 0. It's rule number 1. So rule number 1 just states our horizontal asymptote is y equals 0. Awesome. All right. Our degree of the numerator is 5. Our degree of the denominator is 5. That means they're the same. So if they're the same, that's rule number 2. Rule number 2 states that our horizontal asymptote is leading term over leading term. So we have y equals 9x to the 5th over negative 3x to the 5th. Those cancel out. So we have y equals negative 3. That is our horizontal asymptote. All right, now we're going to work backwards. The red dotted lines, those are your asymptotes. So asymptotes are usually dashed. They're red lines. The graph will never cross your vertical asymptotes. Sometimes it crosses your horizontal or oblique asymptote. I am not going to write that all. So asymptotes are usually dashed red lines. The graph will never cross your vertical asymptote, ever. Sometimes it may cross a horizontal or oblique asymptote. You'll learn that in pre-calc. The asymptote is the exclusion in the domain. And range. I forgot to put that. And range. There we go. All right, so we're going to use the graph to find the domain and range, intercepts, horizontal, vertical asymptote, and oblique asymptote. We're actually going to start in the middle and then work our way down, then back up, if that makes sense. So we're actually going to start at C. So C asks for our horizontal asymptote, if we have any. So we want to look for a dotted line that goes left to right, and we do. We have it right here. So horizontal asymptotes are always y equals, because it goes to the y-axis and it goes through 2. So that's our horizontal asymptote. Now we want to find our vertical asymptote if one exists. So we want to look for a dotted line that goes straight up and down, and we do. It's right here. And vertical asymptote is always x equals because it goes through the x-axis. So x equals, and it goes through 1. So we have x equals 1. Now we need to do part E, which is our oblique asymptote, but we don't have an oblique asymptote. Why? Because we have a horizontal asymptote. So you can't have an HA and an OA. It's one or the other. You can't have both. So we don't have an oblique asymptote. Alrighty. See, that's why we worked that way. That's why we went C, D, E. Now we're going to go to B, then A. So B is asking for intercepts. So there is a point where this crosses right there at 0, 0. Why is it so small? So at 0, 0, the blue crosses the axis. So that means we actually have two x-intercepts because that's x equals 0 and y equals 0. So we have an x-intercept and it occurs at x equals 0, and then we have a y-intercept which occurs at y equals 0. Now let's find our domain and range. So our domain, remember, that's the vertical asymptote. We have our vertical asymptote, it's x equals 1. So that means it's never going to be 1. So that means our domain is x such that x can never be 1, or if you want to write an interval notation, negative infinity 1, union 1 to infinity. So see here, the green highlighted dotted line, you see how it's never, ever, ever going to cross it right here? You see how it's never crossing? Same thing right here, it's never crossing. That's because its x can never be 2. It's never going to cross that vertical asymptote. That's why your vertical asymptote is your domain. Now let's go ahead and find our range. The range, you probably guessed it, it's the horizontal asymptote. Our horizontal asymptote is y equals 2. So that means our range is y such that y can never be 2. Or we can write it in interval notation as well, but I'm not going to. It's the same, just add 2. So see here how it's never, ever, ever crossing here and here. It's never crossing that asymptote, and that's because it's an exclusion in the range. Sometimes you can cross it, but this graph we're not crossing it. All right, let's use the graph to find the same information. We're going to start from C, then work our way. Alrighty, part C. It's asking for a horizontal asymptote. We do not have, oh my bad, we need to add something here that got cut off. Go to the graph and add this little dotted line right here. It got cut off. Alright, so we do not have a line that's dotted that goes straight left to right. So we actually have no horizontal asymptote. For D, we want to look for a line that goes straight up and down. We want to look for a dotted line that goes straight up and down, and we do have that right here. I had to add it because it got cut off. So we do have a vertical asymptote. It's at x equals 0. Because it's right on the 0 line. Alright, E is asking for oblique asymptote, and we actually do have an oblique asymptote. I'll highlight it in yellow. It's this one right here. That is an oblique asymptote. It's diagonal. So since we do have an oblique asymptote, we know that it is y equals ax plus b, so we need to find the slope and the y-intercept, which is the b. So we do have the y-intercept. It's right here. It's 0, 0. And we can find the slope because we can use this point and work and just count. So we go up. So we go up 12. And then we go right 2. So that's 12 over 2 is 6. So we could plug it in. We have our oblique asymptote at y equals 6x plus 0, or y equals 6x. That is our oblique asymptote. Alrighty, B, intercepts. So we're looking at the blue graph. We have x-intercepts at -2 and 2. We do not have a y-intercept. The blue graph does not cross the y-axis at all. Now we can find our domain and range. So remember, our domain is the vertical asymptote, and our vertical asymptote was x equals 0. So that means our domain is x such that x cannot be 0, or -infinity 0, union 0 to infinity. Our range, that's your horizontal asymptote. We have none. We have no horizontal asymptote, so there is no range. And we can also look at the graph, because doesn't it keep going up and down forever? You see how it just keeps going up and down forever? So it's going to go infinitely on the y's. Okay, I'm going to show you a little bit more about asymptotes, but if you're not going into pre-calc or trig, you don't need to know this at all. But if you are, definitely stick around, and I'm going to show you more about asymptotes. Okay, let me switch screens real quick. Alright, so these are asymptotes we found throughout the chapter, or throughout this section. And then we are going to, I'm going to show you what asymptotes look like using Desmos. So I typed the first one in, and remember the first one we found out that it's an oblique asymptote of 3x plus 3. So I actually have that typed in, and I'm going to show you what it looks like. So this is what we're talking about. So we have our rational expression, or function, which is 3x to the fourth minus x squared, x cubed minus x squared plus 1. And then we have our asymptote of 3x plus 1. So our asymptote is blue, and our graph is red. So you see how it does cross. It tell you it can cross, but you see how it just approaches forever? Especially on the bottom one right here. See how it's just approaching forever? That's our asymptote. Let me give you a better example. Let's use one with horizontal asymptote. So I'm going to show you this one right here, the middle one, 9x to the fifth plus 3x minus 11. So I'm going to type that in. Bear with me, it's kind of a pain to type in without an actual functioning keyboard. And I'm just going to pause you guys so you don't have to wait for me. Alright. So here we have our next one, where it's 9 to the x to the fifth plus 3x minus 11. That one where we had our horizontal asymptote of -3. So the red is the function, the blue is the asymptote. So you see how it's just forever approaching the asymptote? Both of them? It's just forever approaching it. That's why we say it's a guideline, because that's what's going to help us guide to that asymptote. Alright, the last one I'm going to show you is x squared minus 25 over x squared plus 2x minus 35. And this is where we found the vertical asymptote is -7. So here, the green is the graph, the purple is the asymptote. So you see how it's never, ever, ever crossing that vertical asymptote? It will never, ever, ever cross the vertical asymptote, okay? Ever. So that's why we say it's a guideline, because if we don't know where we're going, we only have a couple points, we're going to use our asymptotes to finish the graph, or use our end behavior to finish the graph.